Let's talk about the buildings we're in every single day. Our offices, our homes, our schools. We're going to dive into a new technology that's completely revolutionizing how we make sure those places are safe. This is all about automatic building inspection.
You know, it's a question we probably don't think about enough. We just trust that the structures around us are sound. But as our infrastructure gets older, we really have to ask, how do we know? Because the way we've been checking them has some pretty serious hidden flaws.
And that brings us to this really incredible turning point. The old way of doing things, slow, super expensive, and honestly pretty prone to human error, is being replaced by something new. We're talking about a system that's automated, incredibly precise, and completely data-driven. So let's break down what that really looks like.
Okay, first things first, let's really look at the system we're trying to fix. Why exactly is the traditional way of inspecting buildings just not cutting it anymore?
Well, we're basically facing a perfect storm of problems. Manual inspections are so expensive, and they take so long that, frankly, we just don't do them often enough. Plus, there's a shortage of qualified inspectors, and the tools they use can lead to subjective, inconsistent results. And when you add all that up, it creates a very real potential risk to public safety.
So, if the old way is broken, what's the fix? Well, it involves creating a perfect digital copy, a digital twin of a building, and doing it almost instantly.
The key piece of tech here is the Terrestrial Laser Scanner, or TLS. This thing is amazing. It shoots out lasers millions of times a second to capture the exact 3D coordinates of everything it sees. What you get back is this beautiful, incredibly detailed 3D map called a point cloud. Seriously, think of it like a photograph, but with perfect depth and dimension. It's wild.
Now, to really wrap our heads around how powerful this is, let's look at a real-world case study. Some research is focused on just one single building that was in the middle of a renovation.
And in just a matter of hours, their very first scan captured over 312 million individual data points. I mean, that's just an absolutely mind-boggling level of detail. It creates a near-perfect digital replica for them to work with.
Okay, so you've got this gigantic, massive cloud of data points. Now what? How in the world do you turn that into a useful report on the building's health? Well, it all comes down to this really brilliant three-step process.
It's a three-part plan. First, you got to simplify that massive data set, but without losing the important stuff. Second, you assess the geometry of the key structural parts to look for any problems. And finally, you compare scans taken at different times to see exactly how the building is changing.
So, picture this. You're zooming in on just one steel beam inside that point cloud. It's made up of maybe thousands, even millions of those 312 million points. Trying to analyze every single one of those would take forever. It's just not practical.
So, what the system does is pretty smart. It intelligently pulls out a much simpler version, what's called a representative plane, from the most important surface, like the very bottom of that beam. This move preserves all the critical information about its shape and any potential sagging, but in a format that's way more manageable.
And this simplification is just incredibly powerful. By pulling out these representative planes, the system took the number of points it had to analyze from over 100 million down to just 5,000. That makes the whole data processing part nearly 20,000 times more efficient. That's not a typo.
So how do you measure sagging, or what engineers call deflection? Well, the software creates a perfectly straight digital line between the two ends of the beam. It's just like how an inspector would stretch a physical string line. Then it just measures the distance from that perfect line to the actual sag of the beam at every single point. It's a classic, time-tested technique just brought into the 21st century and totally automated.
All right, this final step is where the real magic happens. To compare two scans taken months apart, you have to align them perfectly. So the system uses this super clever technique called semantic-aided registration. You can think of it like facial recognition, but for buildings. It actually learns to identify specific beams and columns, so it can perfectly overlay the before and after scans to spot every little change. How cool is that?
Now, this all sounds great in theory, right? But does it actually hold up in the real world on a messy, active construction site? Let's take a look at the results. So here's the setup. The researchers went in and scanned a building in May, right in the thick of a renovation. Then, for 4 months, all sorts of heavy construction work happened. Demolition, digging, new stuff going up, you name it. Then they went back in September and scanned the whole thing again to see what had changed.
And the results were, frankly, stunning. When they compared the automated measurements to really careful manual ones, The average error for spotting sag was just 1.59 millimeters. Now, to put that in perspective for you, that is literally thinner than a credit card. This isn't just a ballpark estimate. We're talking about incredible precision.
And this right here is where you see the system's true power. It doesn't just give you some overall health score. No, it pinpoints exactly where the problems are. So while most of the beams were fine, the system flagged that a group of transverse beams had sagged an average of 6 millimeters. And it even identified the two specific beams, number 10 and number 31, that had warped the most. This is the exact kind of actionable data that inspectors dream of getting.
So when you put this all together, what does it really mean for the future of our cities and all the buildings we depend on every day?
Look, this isn't just some small improvement. It's a complete fundamental shift. We're moving to a world with millimeter-level accuracy. We're turning days of manual labor into a fast, automated process. This lets us do proactive monitoring, catching tiny problems before they ever have a chance to become catastrophic failures. And that means safer buildings for all of us and huge cost savings down the line.
And this technology really just opens up a much bigger picture. I mean, if we can start giving our buildings these routine, incredibly data-rich health checkups, what's next? What other critical parts of our infrastructure, our bridges, our tunnels, our dams, could we make smarter and safer? That is the really exciting question that we're finally able to ask.